Imagine packing your bags, saying goodbye to Earth, and 3 months later, stepping onto the rusty, alien soil of Mars. Just 90 days to a new world, less time than it takes to finish a university semester. For decades, reaching Mars has meant a grueling 6 to 9 months in a metal can, with all the dangers of hard radiation, bone-wasting microgravity, and the agony of isolation. Now, a controversial new plan claims we could cut the journey in half using the sort of technology we already have, or almost have. But with lives, billions of dollars, and the future of interplanetary civilization in the balance, is this bold shortcut genius, recklessness, or simply a necessary gamble? In recent years, Mars has gone from science fiction daydream to tangible goal. NASA, China, and commercial pioneers like SpaceX are locked in a new kind of race, one defined not just by speed, but by who controls the gateway to the red planet. Why the sudden urgency? Because time and space kills. The longer astronauts spend traveling between planets, the more they're battered by cosmic radiation, and the more their muscles and bones wither in microgravity. Old approaches accepted this grim reality. The best we could do, or so it seemed, was to load up the latest chemical rockets, slog through a half-year journey, and hope the crew emerged with enough health and sanity intact to explore and return. Traditional design ended up bogged down not only by physics, but by the thorny politics and cost of nuclear propulsion. But what if that's all about to change? What if, starting with the upcoming launch windows of the 2030s, human beings can get to Mars faster than ever thought possible, using the same rockets and fuel we're testing today? Here's where things get wild. In a groundbreaking 2025 study, Jack Kingdon, a graduate researcher at UC Santa Barbara, recalculated the basic assumptions. Using SpaceX Starship's next-gen refueling and some clever math, specifically what's called a Lambert solver to plot rapid orbital trajectories, Kingdon found a route to Mars that could take just 90 days. And crucially, he argues, these trajectories could be flown with existing chemical propulsion technology, skipping the need for exotic, politically fraught, and technically undeveloped nuclear reactors in space. Kingdon puts it plainly. This proposal's main advantage is that it only uses technology that exists or is close to existing. VACIMR and NEP are very far from existing for real missions in space. NTP is almost certainly more expensive than chemical, even though the tech does exist, and it does not offer significant advantages. This is a bombshell. For years, the consensus was that only nuclear thermal or nuclear electric propulsion, technologies like NASA's Cold War-era NERVA, or today's demonstration rockets like Draco, could slash interplanetary travel times to the necessary 90 days. These systems promise higher delta V, change in velocity, or specific impulse, but are tangled in engineering, regulatory, and diplomatic hurdles. Giant space nuclear reactors are not something you simply order on Amazon. Yet Kingdon's analysis suggests Starship, with some aggressive in-orbit refueling, could match or even beat nuclear-based timelines. The 2033 optimal Earth-Mars alignment, he calculates, allows a 90-day transit out and a 90-day journey back, using nothing fundamentally more advanced than what's in the pipeline now. To understand the magnitude of this, let's step back. The SpaceX Mars mission plan is audacious. It envisions a flotilla of 6 Starships, 4 for cargo, 2 for up to 200 passengers. These vast interplanetary ships, each a marvel of stainless steel and heat shield tiles, would require a swarm of tanker launches, up to 15 just to fully refuel the crewed vessels in low Earth orbit. The goal? To bring not just explorers, but the machines, habitats, and supplies needed for a true foothold on Mars. Once the Armada arrives, the ships tap Martian resources to make their own propellant, the magic of in situ resource utilization, or ISRU. Carbon dioxide from the thin Martian air, water ice from the regolith, and a lot of chemistry produce the methane and oxygen necessary for the ride home. One cruise ship and several cargo haulers would top off in Mars orbit, collect extra propellant from the cargo ships, and make the return hop to Earth. The cycle would repeat, opening the door, in theory, to life as an interplanetary species. If you're getting excited, you're not alone. But the shorter the trip, the greater the risks, and the wilder the engineering challenges. Moving at higher speeds toward Mars's thin atmosphere, Starship would face brutal re-entry heats and G-forces, testing its ceramic tiles and structure far beyond any Earth return to date. There's no rescue service halfway to Mars. And what about the people inside? Even at 90 days, Mars voyages expose astronauts to agonizing isolation, cosmic rays that slice through cells and DNA, and the slow grind of zero gravity. NASA's limit for astronaut career radiation is just 600 millisieverts. Traditionally, only fast, nuclear-propelled flights could keep exposures below that. Could Kingdon's chemical-propelled shortcut actually keep crews safe? The physical threats are only half the story. Inside the ship, every cubic meter counts. The Starship's habitable volume for a dozen astronauts is on the low end, as Volker Maywald of the German Aerospace Center warns. Will these brave pioneers be able to cope psychologically, packed into a tin can with no escape, and with Earth a tiny blue dot in the rearview mirror? And then there's the communications blackout. At Mars's worst, radio signals from Earth lag by up to 22 minutes, one way. It's like shouting into a canyon and waiting for a reply that never comes. Dana Issei of NASA stresses, communication delays between Earth and Mars necessitate autonomous systems and robust problem-solving skills among astronauts. Any emergency, breakdown, or medical crisis must be handled on the spot. To tackle these gauntlets, the new Mars plans draw on a wave of innovations, many of them, remarkably, already proven or in advanced testing today. NASA's LOFTED project, for example, has pioneered inflatable heat shields, potentially allowing bigger, heavier spacecraft to decelerate safely in Mars's thin atmosphere. SpaceX's own re-entry heat shield tiles have survived 700 kilolars per square meter on Starship's recent test flights. Though Earth and Mars are very different, the supersonic retro-propulsion now routine for Falcon 9 boosters may insulate future Martian arrivals from the worst heating and shock. Radiation, the silent killer, is being tackled from several angles. Stuffed Whipple shields, layered barriers jammed with advanced fibers, can ward off micrometeoroids and cosmic dust. For the deadliest cosmic rays, hydrogenated boron nitride nanotubes offer promising, lightweight shielding. But will these advances be enough, especially if we tack on higher speeds and shorter margins for error? Even the basics of life support are seeing breakthroughs. MOXIE, a compact technology from MIT, has already converted Mars's CO2 into oxygen on the Perseverance rover, pointing the way to scalable, homegrown air and propellant. Michael Hecht, MOXIE's principal investigator, is bullish. Scaling up MOXIE-like systems for oxygen and propellant production on Mars is feasible with adequate funding. If ISRU works reliably, Mars missions can be launched and returned far more frequently and cheaply than previously thought possible. And for power? The Megaflex solar array has surpassed technology readiness level 5, promising ultra-lightweight, flexible solar power for surface outposts and orbital ships. No nuclear reactors required, though they remain an attractive backup in case of Martian dust storms. Of course, the ultimate wildcard for the future is propulsion. Some engineers dream of ultra-fast laser sail technology, whipping tiny probes to Mars in just 20 days. Others hold out hope for denser, safer nuclear reactors or plasma rockets. For now, though, Kingdon's plan bets on what we know: aggressive chemical propulsion, relentless refueling, careful trajectory design, and a blizzard of iterative improvements to ship, crew, and mission architecture. But pause for a moment. If Starship really can reach Mars in 3 months with the technology we have in hand, what's holding us back? Is it the laws of physics, political inertia, or simply the nagging edge of uncertainty that comes with betting everything on a breakthrough? Rob Manning of JPL, who led Mars lander teams, reminds us, supersonic retropropulsion can insulate spacecraft from buffeting and heating during Mars landings. But the unknowns are vast. And then there's the human factor. What will happen when, after 90 days in deep space, the crew stares down a Martian sunrise, knowing rescue is impossible, return is uncertain, and every system in the mega rocket must work, flawlessly, first time, at the edge of the possible? As the 2033 launch window looms, mission planners, astronauts, and billions in investment are converging on a single, haunting question. Can Starship, and the people inside, survive the fastest, boldest Mars journey ever attempted? In the next part of our story, we'll dig into the risks no one wants to talk about, the deadly gaps in our preparations, the ethical dilemmas of a Martian colony, and the unnerving possibility that, even with all our tech, Mars may remain just out of reach. But first, what secret challenge did Kingdon's trajectory calculations reveal about the very design of Starship itself, a flaw that could undo the entire 3-month plan? When you picture the first wave of Starships streaking toward Mars in just 90 days, It feels like the greatest sci-fi leap humanity has ever attempted, all powered by off-the-shelf technology, not mysterious nuclear drives. But as we peel back the hype, what truly lies ahead if this plan works, or if it fails? Let's imagine the future this rapid transit scenario opens up. If Starship really does deliver crews to Mars in 3 months, the implications ripple far beyond the initial mission. A successful fast transit architecture slashes exposure to deep space radiation, a threat so great it has been a showstopper for Mars dreams since the Apollo era. The thin, deadly mist of galactic cosmic rays and solar storms have always haunted mission planners, pushing them toward nuclear propulsion as the only solution. Now, with shorter transits, new materials like boron nitride nanotube, BNNT shielding become viable. Not only are crews safer, but the political headache of launching nuclear reactors is sidestepped, at least for now. With chemical propulsion and orbital refueling, SpaceX's plan avoids the decades-long delays of building and certifying space-rated nuclear reactors. Dana Ives of NASA put it bluntly, "We're at the point where autonomy, robust problem-solving, and speed are not just advantages, they're essentials." But the dominoes start to fall. If Starship can make rapid, reliable round trips, whole new operational models become possible. Frequent resupply means more crew rotations. Early Martian settlers don't have to hunker down for years between ships, and vital cargo, from water purifiers to medical equipment, arrives at the pace of earthly logistics chains. Suddenly, a real, living Martian outpost looks feasible within a generation, not a century. Yet, the very speed that might save astronauts from radiation introduces other hazards. Slamming into the Martian atmosphere at higher velocities puts the integrity of Starship's heat shield to the ultimate test. Jack Kingdon, whose study inspired this fast transit revolution, notes, "We simply don't know at what entry speed Starship or its heat shield will fail. Even SpaceX is guessing." The margin for error narrows as entry speeds rise. A single miscalculation could mean disaster for the crew and the entire mission architecture. Recent advances offer hope. SpaceX's Pika-X heat shield, at just 6 centimeters thick and a feather-light 0.27 grams per cubic centimeter, is rated for punishing re-entry energies, yet Mars's thin air and the unique hypersonic regime pose new unknowns. NASA's lofted inflatable decelerator could supplement Starship's design, providing extra drag and temperature control at Mars. Falcon 9's supersonic retro-propulsion tests on Earth offer more validation, but the Martian descent will be unlike anything tried before. Let's talk about the mass budget, the supposed Achilles heel of fast Starship missions. This is where a hidden flaw could shatter the dream. Every kilogram added for shielding, food, water, oxygen, spare parts, and especially crew comfort chips away at the fuel margin. The mission's math is merciless. Kingdon's proposal assumed a crew complement and cargo mass just within Starship's theoretical limits. But Volker Maywald of the German Aerospace Center warns, the assumed habitable volume for 12 people for 3 months is at the absolute lower end. Any upgrade to shield, supplies, or redundancy balloons the mass beyond what a single Starship can safely carry at high speeds. Here's the invisible razor's edge. The more you pack to keep astronauts alive and sane, the heavier the ship becomes. Heavier ships need more fuel to accelerate and decelerate. More fuel means more mass, requiring even more fuel to move. This is the unforgiving tyranny of the rocket equation. Starship is designed for volume and payload, but Mars fast transit exposes the limits of the system in new ways. Some researchers suggest doubling up on launches or pairing 2 Starships for redundancy, but every solution raises cost, complexity, and risk. The fast transit dream is balanced on an extraordinarily fine edge between speed, safety, and survivability. And what if we push the envelope even further? There's talk of laser-driven light sails slashing transit times to just 20 days. That would be historic, but the technology is even further from reality than nuclear propulsion. Giant space-based lasers, ultralight graphene sails, autonomous robotic pilots, these remain visions for next century. Back in our near-term future, mini revolutions are still possible. NASA's Megaflex solar arrays, now at readiness level 5, could supply abundant, reliable power for life support and systems during interplanetary crews. Communication blackouts will shrink as Starship adopts laser communication relays, solving not just technical hurdles, but also easing the psychological strain of isolation. Astronauts will still face the challenge of up to 22-minute delays in messages, but improved autonomy and AI-driven support systems may keep them safer and more connected. The psychological toll of travel to Mars has always been underestimated. Even on a 90-day sprint, the crew faces months cut off from everything familiar. Michael Hecht from MIT puts it this way: "You can solve the engineering, but the human mind is another challenge entirely. Success on Mars depends as much on morale as on machine." Future missions could leverage these lessons, not just for science, but for shaping robust, happy crews. Pre-mission screening, virtual reality environments, and real-time health monitoring will become as essential as radiation shielding. Down on the surface, ISRU, or in situ resource utilization, will be the make-or-break factor for return flights. Starship's architecture demands the generation of methane and oxygen from Mars' atmosphere and ice, using systems like MOXIE that have only recently been demonstrated at tiny scale. Michael Hecht again. "The tech works. What's needed is funding and the political will to scale it up." If ISRU fails on Mars, every fast round-trip plan falls apart, stranding astronauts or forcing dangerous compromises. There are ethical dimensions too. As Mars becomes more accessible, the risk of contaminating the planet with Earth life increases, a hot topic among planetary protection advocates. If Starship delivers regular rapid missions, new protocols and perhaps even Martian quarantine zones will become necessary. International agreements lag behind this technology race. Regulatory bodies, as the latest report says, often need to get out of the way or risk stifling progress, but proper oversight is vital to prevent chaos on a new world. All of these threads lead to one undeniable truth. The first successful 90-day Starship mission to Mars will not only be a triumph of engineering and ambition, but will also trigger a cascade of consequences, challenges, and opportunities. Some we can predict, some that will catch us off guard. So, what does all this actually mean for us, watching from Earth? Why should you care about the drama of mass budgets and heat shields, the anxiety of round-trip calculations, the political wrangling over nuclear versus chemical thrust? Let's break it down. First, this debate is about more than Mars. It's about how we, as a species, solve massive, tangled problems. The push for faster Mars transits is forcing breakthroughs in propulsion, shielding, closed-loop life support, robotics, and autonomy, fields that will shape everything from climate tech to healthcare, even down here. The materials developed to shield astronauts, like boron nitride nanotube composites, may one day protect patients from radiation in hospitals, or provide ultra-strong, lightweight armor for disaster zones. Second, this is a crash course in creative risk. SpaceX's willingness to attempt impossible missions, using what's available today, not just waiting on tomorrow's tech, shows how audacity and iteration can leapfrog incremental progress. That mindset isn't limited to space. Whether you're building a business, fighting for a cause, or trying to invent something new, the lesson is clear. Sometimes you win not by waiting for the perfect tool, but by daring to reimagine how you use the ones already in your hands. Third, this is a rare opportunity to witness, and even participate in, the creation of an interplanetary civilization. The choices made now, as we solve for radiation, mass, psychology, and supply chains, will shape not just the crews that go, but the kind of world they create on Mars. Will we repeat the mistakes of history, or craft new ways to live together, respecting both the harsh realities of space and the fragile future of two worlds entwined? And here's the secret that rarely makes headlines. The race to solve Mars transit isn't just about speed. It's about building the systems, trust, and knowledge to keep people alive and thriving far from home. Because that challenge will echo again and again, not only on Mars, but wherever humans dare to settle next. So, does a hidden flaw in Starship's mass budget threaten the entire fast transit plan? The answer is yes, but not for the reason most expect. It's not just about kilograms, but about our ability to adapt, improvise, and push through razor-thin margins with resilience, creativity, and determination. As for the other unseen obstacles, they are real, numerous, and formidable. But history shows that every breakthrough comes with new risks, and that the only way to find the boundaries of the possible is to press up against them again and again. The first 90-day Starship to Mars mission might not go perfectly. There will be setbacks, surprises, and perhaps even heartbreak. Yet with every attempt, we learn, iterate, and get closer. And when it does succeed, it will be not just a victory for astronauts or engineers, but for anyone who dares to look up and imagine a different future. If you've made it this far, you're part of this story. The future of Mars won't just be written by rocket scientists and billionaires, but by everyone who cares enough to ask the big questions and demand better answers. So, Keep questioning, keep imagining, and don't forget, the next great leap could start with a doubt, a dream, or a single daring idea. If this breakdown of Starship's fast Mars plan amazed you, share this video, join the conversation in the comments. What would you risk for a shot at the red planet? And subscribe for more deep dives into the cutting edge of